Welcome everyone. My name is Gaurav Tejwani and I am here to present you my ELP 101 project, and the topic I have chosen is instrumentational amplifier. What is instrumentational amplifier? An instrumentational amplifier is a type of differential amplifier that has been outfitted with input buffer amplifier, which eliminates the need for input impedance matching and thus makes the amplifier suitable for use in measurement and test equipments. Before looking at instrumentational amplifier, first we need to look at operational amplifier. An operational amplifier is a DC coupled high gain electronic voltage amplifier with a differential input and usually a single ended output. Here these two are the input terminal and this is the output terminal. The plus side is the non-inverting terminal and the negative side is the inverting terminal. Now, op-amps can be of two types, inverting operational amplifier and non-inverting operational amplifier. In case of inverting operational amplifier, the output voltage is out of phase from the input voltage by 180 degree and the voltage gain is given by minus RF by RIN. In case of non-inverting operational amplifier, the output voltage is in phase with the input voltage and the voltage gain is given by 1 plus RF by RIN. Now, to understand the working of instrumentational amplifier, first we need to understand what is differential amplifier and how it works. A differential amplifier amplifies the difference between two different voltages but suppresses any voltage common to the two inputs. This is the circuit diagram of differential amplifier. Here we can see that it is a combination of inverting operational amplifier and non-inverting operational amplifier. Now we will try to calculate the output voltage. To calculate output voltage, we will calculate the output voltage when V1 is equals to 0, and then we will calculate output voltage when V2 is equals to 0 and add them. Now by Ohm's law, I1 is equals to V1 minus VA by R1 and I2 is equals to V2 minus VB by R2. Also, IR is equals to VA minus Vout by R3. Now, since R2 and R4 are in parallel, VB will be equals to V2 times R2 by R2 plus R4. Now, if V2 is equals to 0, then this is the case of inverting amplifier and the Vout will be given by minus V1 upon R3 into R3. Then Vout will be given by minus V1 into R3 by R1. And if in case of V1 is equals to 0, this is the case of non-inverting amplifier and Vout will be given by V2 times R4 into upon, and Vout will be given by V2 times R4 upon R2 plus R4 into R1 plus R2 upon R1. Now Vout will be equals to minus Vout A plus Vout B. Here minus sign is because the minus sign is there because the voltage is out of phase by 180 degree. Now overall Vout will be given by minus V1 R3 by R1 plus V2 R4 by R2 plus R4 into R1 plus R3 by R1. When R1 is equals to R3 and R2 is equals to R4, this whole quantity will become equal to 1 and Vout will be given by minus V1 R3 by R1 plus V2. Now we will come to instrumentational amplifier. This is the circuit for instrumentational amplifier. Here these two are the buffer amplifier and this is the differential amplifier. The negative feedback of the upper left op-amp causes the voltage at point 1 to be equal to V1. Likewise, the voltage at point 2 is held equal to V2. This establishes a voltage drop across R gain. And R gain is given by V2 minus V1, and since there is no current passing from these two branches, we can apply Ohm's law to give Since there is no current passing from these two branches, the voltage difference from R3 and R4 is given by V2 minus V1 1 plus 2R by R gain. Now, advantages of instrumentational amplifier. We can possess extremely high input impedances on the V1 and V2 inputs because they connect straight into the non-inverting inputs of their respective op-amps. We can change the differential gain of the instrumentational amplifier simply by changing the value of one resistance R gain. The main function of this amplifier is to reduce the surplus that is chosen by the circuit. Thank you.